Good day to all. Today we are going to see about magneto-optic effects. Under the influence of the external magnetic field, the optical properties of certain media are found to change, and these are termed as magneto-optic effects. For example, a block of glass, when placed in a strong magnetic field, develops optical activity. A vapor or a liquid, if subjected to strong magnetic fields, become doubly refracting. These are some of the optic effects that we observed in materials. Faraday effect, Zeeman effect and its inverse, Cotton-Mountain effect, magneto-optic Kerr effect, and Voigt effect. This is the Faraday effect. Faraday effect or Faraday rotation is an interaction between magnetic field and the passage of light through a dielectric medium. Faraday observed that when a block of glass is placed in a strong magnetic field, it occurs the property of optical activity. When plain polarized light is sent through the glass in a direction parallel to the applied magnetic field, the plane of vibration is rotated. The plane of vibration is rotated. The relation between the angle of rotation of the polarization theta and the magnetic field in a dielectric material is theta is equal to VBT or VBL. Sometimes they use instead of T, they use L. V is the magnetic flux density. T is the length of the path. V is the constant of proportionality called Bird's constant. Next one is the Zeeman effect. If a source of light giving line spectrum be placed in a magnetic field, the spectral lines split up into two or more components, doublets, triplets, and even more complex pattern are observed. This phenomenon is known as Zeeman effect. If the magnetic field is very strong, then each spectral line splits into two components, only two components. In the longitudinal view and into three in transverse view. This is called the normal Zeeman effect. That is once again, I repeat, if the magnetic field is very strong, then each spectral line splits into two components, only two components in the longitudinal view and into three in the transverse view. This is called the normal Zeeman effect. When the magnetic field is relatively weak, then each line splits into more than three components. This is known as anomalous Zeeman effect. Anomalous Zeeman effect. Okay. This is the spectral lines of mercury vapor lamp at wavelength 546.1 nanometer, showing anomalous Zeeman effect. Without magnetic field, that is A. Then with magnetic field, spectral line split as a transverse Zeeman effect. With magnetic field split as longitudinal Zeeman effect. Next one is inverse Zeeman effect. Zeeman effect is related with emission spectra, but inverse Zeeman effect is related with absorption spectra. Zeeman effect obtained in absorption is called inverse Zeeman effect. Zeeman effect obtained in Absorption is called inverse Zeeman effect. Zeeman effect means that occurs in emission spectra, but inverse Zeeman effect obtained in absorption is called inverse Zeeman effect. Then now you should know about what is the emission spectra and absorption spectra. So what is the emission spectra? When the energy is absorbed by electrons of an atom, electrons move from lower energy levels to higher energy levels. These excited electrons have to radiate to return to ground state from the excited state, which is unstable. No, so the emission spectrum is formed by the frequencies of this emitted light. This is the emission spectra. So here you can see the spectral lines as the colored one. Then what is the absorption spectra? An absorption spectrum is constituted by the frequencies of light translated with dark bands when energy is absorbed by the electrons in the ground state to reach higher energy states. So here the bands are colored. These places you can get the color here, emission spectra. So dark black bands. Okay. Okay, this is the apparatus of Zeeman effect, and this is in this we can see the Zeeman splitting of spectra. Okay. Then the Zeeman effect obtained in absorption is called inverse Zeeman effect. Then in this effect is observed when white light is sent through an absorbing vapor. For example, sodium vapor. Then this is subject to magnetic field. In the absence of magnetic field, there are certain frequencies at which absorption takes place. After the introduction of the magnetic field, there will be Zeeman splitting of the frequency nu zero, and there will be two resonant frequencies. There will be two resonant frequencies, wise nu zero plus EB by 4 pi m and nu zero minus EB by 4 pi m. As a result, there will be two indices of refraction, two refractive indices. So one outside this region and one inside this region, delta nu. Then hence these two vibrations will move with slightly different frequencies because they have both of them have different refractive indices. No, so these two vibrations will move with slightly different velocities, leading to a rotation of the plane of vibration. Rotation of the plane of vibration. This is what we have studied in Faraday's effect. Okay. Then delta nu increases with B, so will be the Faraday rotation. There. Voigt effect. Next topic is Voigt effect, also known as magnetic double refraction. In 1902, Voigt discovered that double refraction, also known as a birefringence, takes place in a vapor when placed in a strong magnetic field, and light is allowed to pass through the vapor in a direction perpendicular to the field. That is very important. Double refraction takes place in a vapor when placed in a strong magnetic field, and light is allowed to pass through the vapor in a direction perpendicular to the field. Okay, this is known as Voigt effect, or other name is magnetic double refraction. So obviously this phenomenon is related to transverse Zeeman effect. And the same way the Faraday effect is related to longitudinal Zeeman effect. Okay, the Voigt effect is this phenomenon is related to transverse Zeeman effect. because the light is allowed to pass through the vapor in a direction perpendicular to the field. There. Okay. So the Zeeman triplet, the central line nu zero vibrates parallel to the magnetic field and will be absorbed by the electrons in the vapor. The other two lines, this is the central line. The other two lines vibrate perpendicular to the magnetic field. So since these components have different refractive indices, already we know different refractive indices. One component will move faster than the other with a phase difference depending on the length of the vapor. So consequently, we get the elliptically polarized light. So finally, we get the elliptically polarized light. Thank you.